In probability, we try to analyze outcomes of random experiments, for example, rolling a six-sided die. The outcomes lowercase omega of the experiment form the sample space uppercase omega, and subsets of the sample space for which probability is defined form the events. For example, we can say that the face with 2 pips is one of the outcomes. To analyze the experiment mathematically, we need to convert outcomes to numerical values. We can do this by introducing a random variable function, which takes in an outcome and returns a numerical value. In this case, if the outcome is the face with n pips on it, then x evaluated at that outcome will be the real number n. Now that we have a mathematical model, we can look at some properties of the probability distribution. One of the most important concepts is expected value, which is a single value that captures average or long-run behavior of the entire distribution. In the case of rolling a die, the expected value is 3.5 or 7 on 2. Rolling a die 1,000 times will indeed result in approximately 7 on 2 times 1,000 pips overall. In the discrete case where there are finitely many outcomes, the expected value is a weighted sum, namely, the sum of values weighted by their probabilities. For example, rolling a die gives the numbers 1 to 6 with probability of 1/6 each, and the expected value is hence 1 times a 6 plus 2 times a 6 all the way up to 6 times a 6, which gives 7 on 2 as expected. Sometimes there are conditions imposed on the outcomes, and in this case we would get what is called a conditional expectation. If we are told a roll is prime, then we should restrict the possible outcomes from the entire sample space to the smaller event A containing outcomes 2, 3, and 5. Conditioning on A gives the expected value of x given A to be 2 plus 3 plus 5 divided by 3, which is the number of elements in A. Now suppose that we have another random variable y, which counts the number of letters in the value. Knowing y restricts possible outcomes for x, so we can also condition on y to get the random variable expected value of x given y. For example, if y equals 4, then the possible outcomes are restricted to 4 and 5, which both have 4 digits, so the expected value of x given y equals 4 would be 4 plus 5 divided by 2. Once we calculate the conditional expectation of x for each value for y, then we can fully describe the random variable e of x given y. Now we can start trying to understand some important results in probability theory. The law of total expectation states that taking the expected value or averaging a conditional expectation e of x given y gives a total expectation e of x. Although not a proof, one way to visualize this is as follows. Say our random variable x is the value of a die roll, and y is the number of letters in the value of a die roll. We can visualize the interaction between x and y in a table. The conditional expectation e of x given y is given by looking at each set of outcomes of the same y value and averaging the values of x evaluated on those outcomes. We can imagine the outcomes as blocks of gold with their height given by x. Finding the conditional expectation e of x given y is like melting down the gold blocks and letting it flow through the columns with the same value. Then we can think of averaging the conditional expectation as letting the gold flow between all of the columns. The new height will be e of x given y. But finding the expected value for x is like melting down everything from the start, skipping the intermediary step. We can see that the end result will be the same. After all, we couldn't have lost or gained any gold. To visualize linearity of expectation, we can try to answer the following question. Roll a die n times. What is the expected number of unique digits? What we can do is consider every possible outcome from all 1s up to all 6s. For each outcome, count the number of unique digits, multiply by the probability of the outcome 1 on 6 to the n, and sum up all 6 to the n values. As it turns out, this is not the most efficient way to solve the problem. We can utilize an important property of expectation, namely that it is linear. This is sort of like saying that averaging the sum is like summing the average. Let's visualize all of the outcomes when n equals 2 side by side. Notice that every value from 1 to 6 contributes +1 to the total number of unique digits in an outcome if it appears, and 0 if not. We can express this mathematically using indicator functions. If S is a set, then the indicator function of the set, evaluated at an outcome, is 1 if the outcome is in the set, and 0 if the outcome is not in the set. Note that indicator functions behave like random variables, converting outcomes to numerical values. The number of unique digits in any particular outcome can be quite nicely represented as a sum of 6 indicator functions. Then we can write the quantity we are trying to find in the following form. Here is an opportunity to remember that expectation is linear. The expectation of the sum equals the sum of the expectations. Visually, this means it is possible to decompose and reorder the values without changing the end result. To evaluate the expected value of the indicator function on the set of outcomes containing the digit I, we can count all of these outcomes and divide by the total number of outcomes, or equivalently, count all the outcomes not containing I and subtract from the total. Then after some algebraic manipulation and generalizing from 2 to n, we can get the final solution of 6 minus 6 times 5/6 to the power of n.